To move on from dyadic metrics into the triadic metrics, you have seen some indication of what triad census represents. When you run triad census command over a network object in iGraph, it's going to return a vector of 16 numbers. And what those numbers actually mean is the number of triads of a certain type. So here you have a little cheat sheet. So with the first number is going to refer to the number of empty triads in the network. So we know that that's a really high number, right? So A, B, and C, and there are no ties between one another. The second, well, let's start from the bottom, right? The very last number, number 19 in this vector, represents this type of triad, so where all the three nodes are fully interconnected, and we have 19 triads like that in our network. The sort of the 15th element in this numeric vector shows 63, so we have 63 types of dyad of this type, or of this kind, and that is the dyad where A is connected to B. So we only have one direction between A and B, but B and C are mutually connected, and A and C are mutually connected. So in our network of Desert High School, we have 63 dyads of this kind. Another interesting and quite useful descriptive metric of the network level is transitivity. So let's just sort of remember that we can always check what that command is, and it measures the probability that the adjacent vertices of a vertex are connected. Or in other words, we're looking at the clustering coefficient or the ratio of the triads, closed triads, clustering, the ones that are going to cluster, the closed triads within the network. So to learn the transitivity of the network, we run transitivity command over a network. We specify that the type of transitivity we're interested in is local, so we want to see the embeddedness of each node. And so let's just run this, and what you see it returning is a vector, which basically is a number that refers to embeddedness. I'm just going to plot this network quickly here to remind you what it looks like. Desert High School, right? So there's a lot of stuff happening, but what this does is it looks at each individual node. So let's say node 62. It's probably this one. No. Yeah. So let's say, right, 29. It's definitely looks like this, right? 29, and here we can see that it does not have a clustering coefficient because it's not embedded within any of the triads. But some others have higher local clustering coefficient or transitivity, which means that they're embedded within a number of triangles. So they are embedded within a cluster. We could calculate the same metrics at the level of the entire network, not at the level of a node. We just need to specify that the transitivity we're interested in is global, and that returns 0.26. So to continue, there are a few things you can do with transitivity, and you should sort of be aware that it's often associated with network closure, and network clustering is, especially if the networks refer to human activity, is something that is common to observe. So that means that social processes are taking place. So we can ask very different questions around the closure in the network, just like we have been able to ask different simple questions around associativity. So one of them is, for instance, we can wonder how embedded or sort of cliquish on average are nodes of a certain kind within a network. So for instance, do boys tend to be more situated within groups than girls? So to look at that, I'm going to show you how one way of evaluating that. So just to remind you, this is our network, Desert High School network, 107 nodes, and it has a variable called sex that looks at gender. So we're going to just look at that vertex again. You can see that it's coded 1 and 2. So we know that, let's say, 2 refers to boys and 1 refers to girls. Actually, I don't remember exactly what refers to what. So we'll find out shortly. And what we do here is that we run the transitivity command just in the same way as we have done that before. We want to see a local clustering coefficient per node, but we only want to do that for nodes that have that are assigned category 2 in the vector that talks about that refers to gender. So this command should return a vector. You can see that this vector is shorter than the one we had before. If I so this was our, just let me rerun this command for you. So we know that it's 107 nodes in the network, right? So if we run transitivity only for those that had 2, we have a shorter vector. And we also see that some are more embedded than others. We can also retrieve the similar vector for all the girls. So we just change that the value that we're interested in keeping for the nodes is 1 in a vector that refers to the attribute sex assigned to vertices of a network IFDH, which is a Desert High School. But that really doesn't tell you much, right? So what you could then look is you may want to look at the mean of all the clustering coefficients, right? So if I just run mean over this same command that referred to boys before, let's see what happens. It's not going to work, but we'll see why. So it returns an NaN, which is because you can't really calculate a mean over something that has NAs or non-applicable, non-existent values within a vector. So to calculate the mean within all the real values, so sort of all the values that are numbers within this vector, we're going to run a command that will calculate the mean of all the values. But it first will omit all the NAs. So the way this command is easiest to read is like that. We are going to calculate transitivity of a network, Desert High School network. It's going to be local transitivity for each node, but only for those nodes where the gender in the attribute vector refers to 2. And then when that vector is generated by this command, we're going to omit all the values that are NaN, non-existent. And then once those NAs are omitted and we have only the values that calculations can be done on, we're going to calculate its mean. So let's look at the mean of how embedded the boys are, and we have clustering coefficient of 0.24, and we can look at how embedded the girls are. And the girls seem to be, I guess, tried, because the girls should be a little bit more embedded in the sense that the girls may be more sort of hanging out more together. We can do something similar looking at race, so how embedded or how big are the cliques based on race. So just to remind us how it was coded, because we don't remember, so we have some different letters standing for a race, so clearly that's O is other. And we have Asian and white and black. And so here we go. We run the 2, looking at the different ones, and we can see that we have a lot more cliquish activity here than here. So we can argue that there are some social processes happening in this network, right? We've seen that the assertivity based on grade is quite high, but the assertivity based on degree is low, which means that people don't really hang out with other popular people, but they hang out based on some other unknown attributes, possibly grade. But we also can see that there are some sort of, there's a high clustering, or sort of there's some embeddedness around gender, and there's some embeddedness around race. So we can assume that there are things happening in that network that we can then further down the way, after exploratory, these descriptive analysis that we're looking at right now, that are also telling, we can actually do statistical modeling later.